Welcome to this video where we're going to explore the factor theorem and using it to solve cubic equations. Okay, so the factor theorem is stated here. Here are some examples of cubic functions that have been plotted. You'll notice they all have rotational symmetry of order 2. Okay, and also they all cross the x-axis at least one place, meaning there's at least one real solution to all of these cubic functions equaling 0. There's one there, that function has a solution there. This one has 3 solutions, or 3 roots, there, and there. And this one has 2, because one of them is where it crosses, and this is where it touches the x-axis but doesn't cross. That's called a repeated root. Okay, so there we have 4 examples. These have an x cubed term that's positive, so the graph runs from bottom left to top right. If it started with a negative x cubed term, it would run from top left to bottom right. Okay, so how do we use the factor theorem to solve a cubic equation? Well, let's have a look. I'll first of all take these off the screen to give us a bit of space, and we'll introduce an example of a cubic function. There it is. And we're going to start by finding one value of x that solves the equation f of x equals 0. So this is the equation we're trying to solve, f of x equals 0. And at this stage we don't know whether it's got one solution, 2 or 3. But we'll find out in due course. So we need to find a value of x that will solve that equation to start us off. Now, normally if they're asking you to solve it from scratch, there'll be an obvious value of x which will be either 1 or 2 or -1 or -2. Okay, if it's something more obscure or further away from 0, they would normally give you an indication of what that is to get you started. But in this case, we can see that if x was -2, it would actually work. So when x is -2, okay, we get that f of x is 0. Okay, I'll just show you the substitution because it's 6 lots of -2 cubed, okay, which comes to -48. Plus 11 lots of -2 squared. Okay, -2 squared is 4, so that's 44. The next part is -3 lots of x, which is 3 lots of -2. Okay, which is +6, and then -2. And if you check that out, you can see that that does come to 0. So we know for sure that x equals -2 is one of the solutions to that cubic equation here, equaling 0. And we also know, therefore, that x minus p is a factor. Okay, so because our solution, our p is -2, x minus -2 is x plus 2. So x plus 2 is a factor. So that's what we call one of the linear factors of that cubic function. Okay, so what I'm going to do, I'll just put that in brackets because we often write factors like that. I'm going to use long division first to find the remaining factors and solve it. Okay, so this is by long division. So I'll show that first. So x plus 2, I'm going to divide that into the original function, which is 6x cubed. Okay, I'm leaving a bit of space between each term, plus 11x squared minus 3x minus 2. Okay, so this is a long division, and we put a bar across there like that. We just extend that bracket at the front to the top like that, and we just do a long division. So we say, how many times does x plus 2 go into 6x cubed plus 11x squared? We just look at the left-hand term, the x and the 6x cubed, so it goes in there 6x squared times. You can write that there or there. It doesn't matter as long as you move along one place each time. 6x squared times x plus 2 gives me 6x cubed and 12x squared. So I write that underneath like that, and then I do a subtraction. Okay, so this is algebraic long division. Plus 11x squared minus 12x squared is going to be minus 1x squared, or just minus 1. I'm going to write minus 1x squared. It's probably easier to see what's going on there. And then I'm going to bring down the minus 3x from above, like that. And now I'm doing another division. I'm saying, how many times does x plus 2 go into minus x squared minus 3x? So basically, how many times does x go into minus x squared? Well, it goes minus x times. Okay, and minus x times x plus 2 is minus 1x squared. Okay, and then minus x times 2 is minus 2x. I do another subtraction to see what's left over. So I bring that across there. Minus 3x take away minus 2x is the same as minus 3x plus 2x, which is minus 1x, or just minus x. Bring down the minus 2, and now we should find that this goes exactly into this. There should not be a remainder. And the reason for that is because of the factor theorem. Okay, we found a value of p, which caused the function to equal 0. Then if x minus p is a factor, it means it goes exactly into the original function without a remainder. So it does indeed. So x plus 2 into minus x minus 2 goes exactly minus 1 times. Minus 1 times this gives me minus 1x. Minus 1 times 2 gives me the minus 2. And to conclude, I can show that the remainder, when you subtract, is 0. So it does indeed go exactly. And what that means is that our original function f of x can now be written as a linear factor, which is x plus 2, multiplied by a quadratic factor, which is 6x squared. Okay, taking the answer to our division here, minus x minus 1. Okay, which means that if you took those two brackets and multiplied them together, you would go back to our original cubic up here. All right. And then what we do is we would work on this and factorize this quadratic to get the other two linear factors. But what I'm going to do first is show you a different method of doing this completely. But before I do that, I'm going to just take out the x's and show you another way you could present this. So you can see it's a lot less cluttered without all the x's, but we still end up using the same method and getting the same result there. Okay, and the process we've used here is called algebraic long division. So I'll just label that for you there, and that's what we've done over here. Now, a completely different method of getting the second part here, okay, is to use equating coefficients, which is what we're going to do over here. Okay, and both methods have their advantages and disadvantages, and there are times when one method is more appropriate and useful than the other. So let's see how that would work. So what we do is we say, well, we know that x plus 2 is a factor. So what we're going to do is say, well, if x plus 2 is a factor, then we know that x plus 2, okay, times by some unknown quadratic, okay, and the unknown quadratic, okay, we know what it is now because we've done it here, but if we didn't know, we would just call it ax squared plus bx plus c. Okay, ax squared plus bx plus c. And we know that if we multiplied those two things together, we would get our cubic expression, our cubic function, which is 6x cubed, okay, plus 11x squared minus 3x and minus 2. Okay, so what we do now is we expand this bracket out, so that will be basically you're taking each term in here and timesing it by x, then each term in there and timesing it by 2. So there'll be 6 terms altogether, which will condense into 4. So we're saying that ax cubed, okay, plus bx squared plus cx, and then we've got plus 2 lots of ax squared. We've also got 2 lots of bx, and we've also got 2 lots of c, and we can say that all of that is equal to what we have here. Okay, like that. All right, so the next thing we do is we collect together what we call like terms. So we have one x cubed term, which is ax cubed. Okay, we have 2 x squared terms, and that's b and 2a. So if we add them together, we get b plus 2a lots of x. Okay, we also have 2x, x squared, that should be. We also have 2x terms, that's c and 2b. So we have plus c plus 2b lots of x. And finally, we have our 2c on its own at the end, which is just a number. Okay, and so equating coefficients means that we literally look at the x cubed, x squared, x and number coefficients and just match them up. So it's simply this. So what I do now is I say that the ax cubed equals 6x cubed. So for sure, I can say that, I'll just highlight these in different colors. So for sure, I can say that the a there must equal the 6 there. All right, so I can write that a equals 6. I'll just write these over here. Okay, and now I'm going to do looking at the c term, and I can see straight away that the 2c at the end, the plus 2c, is the same as minus 2. In other words, the number at the end of this is the number at the end of that. Therefore, 2c is minus 2, so c must be minus 1. Okay, and now in a different color again, we will look at, say, this term here. We can look at the b plus 2a, okay, the b plus 2a, and we can match it to the 11 here. So the x squared coefficients are the same, but we know that a is 6, so b plus 2a is 12. So we can say that b plus 2 times 6, right, is the same as 11. We know 2 times 6 is 12, so b plus 12 is 11. So therefore b must be -1. Okay, so b is -1. And that's it. I found them. I didn't need to use this at all because I had enough information from the other bits by equating coefficients. So it's a very neat, quick way of getting the values of a, b, and c. And we can see that a is 6, b is -1, and c is -1, which is exactly the same as what we found here. 6 minus 1x minus 1, you see. So either way, we end up with this same expression here for f of x. So what I'm going to do now is continue this on from here. So at this point, these two methods merge together to give us the same result. And from here, we now factorize the quadratic. And we can see that x plus 2 is at the front, and we're told that it factorizes in the question. It will say factorize fully or solve this cubic. So the next job is to try and factorize the quadratic into 2 pairs of brackets. Well, there's several options here. It could begin with 6x and x, or it could begin with 2x and 3x. And a little bit of exploring would show that it's 3x plus 1 and 2x minus 1. Okay, because remember the plus 1 times the minus 1 would give you the -1. The 3x times 2x would give you the 6x squared. To get the -1x, we've got minus 3x here with the outer term plus 2x, which indeed gives us -1x. So that's what the function is. And for it to equal 0, okay, because that's what we're trying to do, solve the equation f of x equals 0, then clearly x can either be the number -2, which causes this bracket to be 0. It can be -1/3, which would cause the middle bracket to be 0, or it could be 1/2, which would cause this bracket to be 0. All right, so basically for a product of 3 brackets to equal 0, any one of those brackets needs to be 0 to cause the whole thing to be 0. And those are the 3 values of x that make that happen. So those are the 3 roots or solutions to the equation 6x cubed plus 11x squared minus 3x minus 2 equals 0. And if you plotted the graph of this function, you would see clearly those 3 roots. And I'll just bring that up now so you can see that. There it is. And if I just make that a little bit smaller, no, it's clear enough. You can see it from there. We've got our 3 solutions shown clearly. So the first one is the -2, which is here. The second one is -1/3, which is that point there. And the third one is +1/2, which is shown clearly halfway there between 0 and 1. And that is our cubic that's been plotted. Notice that the axes have been stretched a bit. The x-axis is more stretched out than the y. This tends to often be the case when cubics are sketched to show the shape more clearly. Okay, I hope that was helpful. Take care.